In this video, we're going to be talking about how Bohr's experiments with light managed to bring us from the Rutherford model of the atom that we were working with previously up to a newer model of the atom, which is the one that you are familiar with from your biology classes last year. Again, you'll need something to write on and something to write with, and once you have those ready, let's go. So we'll just start off with a little bit of a review of atomic structure. So what we have here is the Rutherford model of the atom. Right, the Rutherford model of the atom, you have two different regions. You have the nucleus, which is in the center. It has almost all of the mass of the atom because it contains the protons and the neutrons. And then you have the electrons, where each electron is in its own individual orbit around the nucleus. Okay, so this is Rutherford's model. Bohr, who was a student of Rutherford, then extended this model after doing some experimentations with light. So we'll talk about these experiments. To start off with, let's just say that you take light and you shine it through a prism. So you take sunlight, for example, and you shine it through a prism. What do you get? You get a rainbow. Right? You can see this happen all the time after it rains. The water droplets work like a gigantic prism. It separates the light into its individual component colors, and you have your Roy G. Biv. This rainbow is what we call a continuous spectrum. The reason why is that all the colors bleed into each other, so there are no empty spaces. It's just continuous, one color to the next, to the next, to the next, to the next. Alright, so this is what happens with regular sunlight, or what we call white light, when you shine it through a prism. Well, Bohr decided, well, why don't I try shining light from hydrogen gas through a prism and see what happens? So he made a lamp. He filled the lamp with very low pressure hydrogen gas, turned on the electricity, and it glowed a color, and he shined that light through a prism, and he saw something that was slightly different. Instead of getting this constant rainbow, one color bleeding into the next, into the next, into the next, what he saw were just a series of individual lines. Right? And then there's a lot of spaces in between these lines. This is what we call a line spectrum. So for hydrogen, what I have up here on the slide is the line spectrum for hydrogen. These are all of the lines that you see, all the different colors that happen when you shine hydrogen gas, light created from that, through a prism. Now, the interesting thing is that this pattern happened no matter which element Bohr used to create his lamp. Right, so the same thing happened where you got this line spectra. The only thing is that different atoms produced different lines. Okay, so hydrogen produced its set of lines, helium produces its own set of lines, lithium produces a third set of lines. Every element produces a set of lines. Now, the reason why this happens is because atoms have to have energy states that are specific to that atom. That's the only way that each atom can create its own set of lines. Now, in order to explain how this works, you need to think about energy states. Okay, so electrons normally exist in what we call a ground state, which is a low energy state. If you add energy to them, for example, if you pass electricity through them, which is what Bohr did, or if you light them on fire, which is what we're going to do in the lab, then you will raise them to a higher energy state, which is called an excited state. Now, the excited states are unstable. Electrons aren't going to stay there very long. And in order to go down from its excited state back to the ground state, it has to give off the energy that it absorbed. The way that it's going to give off that energy is usually as light. And the amount of energy that it gives off correlates to a color, as we saw from our different wave equations before. Okay, so blue light correlates to one wavelength, one's energy value. Red light correlates to another energy value, which is another wavelength. And they are specific to that element. So this is why we see this line spectrum. This is also why in the lab we see elements burn different colors, because it's different combinations of energy gaps that you have to jump back down from in order to get to the ground state. So to describe Bohr's model of the atom, basically what he did was he took Rutherford's nucleus, kept it the same. But instead of each electron orbiting the nucleus in its own individual path, he changed that to create energy shells, the rings that you had to draw last year when you were drawing atoms. Right? These rings are what we call energy levels, or more commonly referred to as energy shells, where the electrons are. Each energy shell can hold what we call 2n squared number of electrons. So the first ring is n equals 1. 1 squared is 1 times 2 is 2. First energy shell holds 2 electrons. The second energy shell, n equals 2. 2 squared is 4. 4 times 2 is 8. So that holds 8 electrons. Right? So remember last year when you were drawing in the dots, you drew 2 in the first ring and 8 in the second ring? This is why. Because each energy shell can hold 2n squared electrons. Now, the farther away an energy shell is from the nucleus, the higher the energy of the electron. Right? So higher energy electrons are allowed to be farther away from the nucleus than lower energy electrons. They're not caught by the positive charge of the nucleus as much. And to transfer from a lower shell to a higher shell, or from a higher shell to a lower shell, an electron has to gain or lose a very specific amount of energy, and that energy is equal to the energy difference between those two shells. Okay, so what we have here is a diagram of the Bohr model. If one of these electrons in the first shell wanted to jump up into the second, it has to gain exactly the amount of energy that is the difference between the first and second shells. If that happens, then it will jump up into the second shell. If it gains more energy, it may even find a way to climb up into the empty third shell. Right? All the different energy shells exist, even if they don't have any electrons in them at the time. If you gain enough energy, it can jump higher and higher and higher and higher. So this is the Bohr model of the atom. Electrons can transition between different energy states. When they do so, they will either absorb or give off certain amounts of energy. Usually when it gives off energy, it's in the form of light, and you can see that light manifesting as different colors specific to that element. Okay, so that is the Bohr model. In the next video, what we're going to start covering is we're going to break this Bohr model up and get a little bit more modern than this, but not very much. And we'll finally figure out how the electrons start filling into the atoms a couple of videos from now.